Welcome to solverfy.
In this question, we are setting up an RC circuit as shown in the figure, and then we're going to close the switch and investigate the charge versus current relationship for this circuit. So why, when we have plotted our data, does it look like, actually before we dive into why do these data points look like this, let's go ahead and answer the part that asks about the slope and intercept, because I plotted this in a program called graphical analysis. And it gives me the slope and the intercept right here, but they are very small and hard to read. So my slope is going to be negative 1.248 microcoulombs for every milliampere. And my y-intercept is 79.9 microcoulombs. I don't like the way that excuse me, I don't like the way that 9 looks. All right, so now we're going to answer the question. And I'm going to type down there at the bottom underneath the images just because it will be easier to read than my handwriting, and I can go faster than writing by hand. And so these data fall near a straight line because the current is the time rate of change of the charge. The current is the greatest just after the switch is closed when the charge is 0. And as charge builds on the capacitor, it pushes back against the flow from the battery, and the current decreases. And then the longer that charging goes on, the longer it takes to push the same amount of charge onto the capacitor plates, resulting in a decreasing rate of change. And when the capacitor is fully charged and at the same potential as the battery, the current drops to 0 as no more charge can be moved. So, the charge and the current both rely on the same e to the negative t over RC, and that also plays into it. But this is the best way to explain when we remove time as a variable, when we set up these these two quantities as a relationship with each other, why this happens. And so now, use our results to calculate the resistance of the resistor and the EMF of the battery. Well, I actually found it easier to do the EMF of the battery first, because we need to note here in part B, that our resistance of the resistor can be found from the initial current equals the EMF divided by the resistance. So our resistance will be equal to the EMF divided by I naught. And we're going to have to find the EMF first. And then we are also going to need to get I naught is, of course, the current right at the start when charge is 0, which is going to be that y-intercept. And we can actually use the slope and intercept from our linear fit to get a precise value for that. So we're going to have to come back to current. Let's go ahead and, how about purple? Because I've already done a bunch of typing in blue. So here's where we can look at the fact that our Q final, really it's our Q final, our final amount of charge is going to be equal to the capacitance times the EMF of the battery. And so we can find the EMF of the battery with the final charge divided by the capacitance. Well, the final charge is just what happens. We're looking at when current has dropped to 0. And that's going to also be the same as our y-intercept. And so that was 79.9 microcoulombs, so I need to put it as 10 to the negative 6, divided by a capacitance of 5 times 10 to the negative 6 farads. So that gives me an EMF of 15.98 volts. And now, here's the thing to remember. One, this is the result of a linear fit to data. I think it's more likely that it would be 16 volts. And just practically speaking, we actually would say that the capacitor, the charge of the capacitor approaches that of the battery, and the current approaches 0. What happens is the time for a noticeable change just becomes so very, very long that it's not really measurable. So we're just going to go ahead and let this EMF be 16 volts. So we're going to take that 16 volts and come up here to that resistance calculation. But like I said, we are going to need to figure out what is that x-intercept. So what is the current when charge is 0? So we'll take, I'll go a little bit lower down so I'm going right. So we'll take that charge equals negative 1.248I plus 79.9. And again, we're looking at when is charge 0. What was that value of the current? So I'll plug in 0 for charge, and then rearranging, I'm going to get that current I is 79.9 divided by 1.248. And I get, so this is again, that's going to be my I naught. I really could change it here in this level to be I naught. Negative 1.248 I naught plus 79.9 equals 0. And so I naught is going to be 64 milliamps. So we will go plug in our 64 times 10 to the minus third amperes up here. And that is going to give me a resistance of 250 ohms. And after what time, or what time t after the switch is closed, will the voltage across the capacitor equal 10 volts? Okay. How about orange? Or we can write in black. I don't use black very often because there's so much text that goes in black. We are going to need to look at how do these relationships allow us to get to V equals 10 volts, because we have an equation that says that charge equals the capacitance times the EMF times the quantity, 1 minus E to the minus T over RC. And then we're going to remember that since capacitance is defined as charge per volt, we can say that the voltage will be equal to the charge divided by the capacitance. So we are basically going to take this equation and divide it by the capacitance to get a relationship for voltage. So my voltage is going to be equal to the EMF of the battery times the quantity, 1 minus E to the minus T over RC. We're going to need to calculate, well, what is RC? That's going to be my 250 ohms times my 5 times 10 to the negative 6 farads. And I get RC to be 1.25 times 10 to the minus third. And that time constant either has, I can't remember if it has units of seconds or no units, but it doesn't matter. We're just going to plug it in anyway. So from here, we can now say 10 volts across the capacitor equals 16 volts of EMF on the battery times the quantity 1 minus E to the minus T over 1.25 times 10 to the minus third. And so 10 over 16 equals 1 minus E to the minus T over 1.25 times 10 to the minus third. And that gives me 0.375 equals 1 minus E to the minus T over 1.25 times 10 to the negative third. And so I'm going to subtract 0.375 from both sides and add that value for E. And I'm going to go ahead and come over here to the left. So E to the minus T over 1.25 times 10 to the minus third equals 1 minus 0.375. And from here, we will take the natural log of both sides, which leaves me with negative T over 1.25 times 10 to the minus third. Oh, actually, I am so sorry. 10/16 is not that 0.375. 1 minus 10/16 is what we get. But let me fix that. Yeah, let's fix that. The 0.375 belongs over here after we have done our subtraction, and then 10/16 is 0.625. Okay, that makes a little bit more sense. Yeah, so now when I move things around, this is what I get. And I have negative T over 1.25 times 10 to the minus third equals the natural log of 0.375. And so my time T will be equal to negative 1.25 times 10 to the minus third multiplied by that natural log of 0.375. And I get 1.226 times 10 to the minus third seconds. So it doesn't take long at all for the voltage across the capacitor to reach 10 volts. And finally, part D. At what time after, or when the voltage across the capacitor is 4 volts, what is the voltage across the resistor? No, I don't write in red very often, so we'll use red for this one. Well, here's the thing, guys, is that the EMF will always be equal to the voltage on the capacitor plus the voltage of the resistor. So our voltage across the resistor at any time will be equal to the EMF minus the voltage across the capacitor. So we can take our 16 volts minus the 4 volts given, and that's going to give us 12 volts across the resistor.